We have already obviously wrapped up exam number 2 material. Homework number 10 will be comprised of today's lecture, where I'll talk about rotational kinetic energy and angular momentum, as well as the 2 videos that I posted for you to make up for the fact that I missed last Thursday. So please watch those on your own time. It's the topic of simple harmonic motion. If you have any questions on that, you can email me. You can even email the exact timestamp where you wanted to follow up on something or didn't hear what I said, and let me know if you have any questions. So I think those lectures are maybe 100 minutes in total, which is maybe 15 minutes longer than the one lecture I missed, but I talk slower for undergrads, so that kind of works out in the wash, okay? Okay, any quick questions before I get started? Okay, so let's talk about our rotational kinetic energy. This is basically a topic that is belongs quite at home with the rest of the rotational unit that we've been talking about. The cutoff for exam 2, I don't want to include all of it on all of the rotational unit here. So first of all, what do we know about kinetic energy? We have good old 1/2 mv squared. And at this point, we will realize that we should probably call this translational kinetic energy. This is all the old physics. Now we're going to have new corresponding physics as well. And there's really only one point this is good for, the center of mass. So if you want to talk about the translational kinetic energy of an object, you use the entire mass of the object, and you use what is the center of mass speed. Center of mass is always the ambassador for linear physics. And then we have to recognize that there's another way that you can have energy in your motion. That's rotational kinetic energy. And just to cut to the chase, rather than prove this to you, I'm going to tell you that the correct answer for this formula can be found simply by replacing all the variables with their angular counterparts. Okay? So we have 1/2 times, and what's the rotational analog to m? I, and how about v? Omega. So if I were to laboriously do a proof, well, it would take all of 5 minutes, but it's not particularly instructive. Then we would find that there's another place that you could have energy in rotation. So motion energy in rotation. So let's take a look. We have an object like so. So this thing could be flying through space. It could have center of mass speed. And we go to our original formula and we say, of course, well, if you go faster, the center of mass is traveling faster, you have more energy in your motion. And it's not just about speed, but also mass. So if you have a more massive object going at the same speed, it still has more energy. So the example I gave before was that if you have a truck going at 50 miles an hour, it has more kinetic energy than a mosquito going 50 miles an hour. Okay? So it's about how much mass you have and how fast is that mass going. Well, now that we have an extended object, it could be rotating as well. So that addresses the rest of the object. The faster it's rotating, the more energy is contained in the rotation. So something spins really fast, it's going to have more rotational kinetic energy. And also, for a given rotation rate, for a given omega, if it has more rotational inertia, it has more energy stored in that motion. Okay? So more energy manifested in that motion. So everything's perfectly analogous, and I do want to point out that generally speaking, the center of mass speed and the rotation rate around it are independent. So v, COM, and omega are independent generally. So if I take an object, it can only be translating, so it can just be moving through space. That's the old kind of kinetic energy. It could only have rotational kinetic energy, but its center of mass staying put. Okay? It could be any permutation thereof. It could be rotating slow but moving fast. It could be rotating fast and moving slow. Right? So these are independent things. Okay? One of which in particular I want to put down here, where let's say that it's only rotating, but its center of mass stays in place. So it looks like that. Okay? So there we have to, of course, acknowledge that there is some kind of energy in that motion, and it's not the old kind of kinetic energy we used to have. It's energy of the object rotating on itself, not of the whole object flying through space. Okay? So from here, while these are independent generally, I'm going to look at one very specific kind of motion where you do have both of these types of energies and they are related to each other, and that's rolling. Okay? So that's probably the most important situation where we have both kinds of energy. So I want to point out, when something is rolling, okay, its center of mass progresses forward, and its rotation around the center of mass occurs too, right? And I want to point out that if the center of mass moves more slowly, the object also rotates more slowly, but when the center of mass moves faster, it also rotates faster. So in rolling, there is a specific relationship between these two. So in rolling specifically, there is some connection between these two, and we're going to find out what it is. So in rolling, you have both of these kinds of kinetic energies, and there is some sort of relationship between their ingredients. So let's go ahead and draw something in the process of rolling. Seems like there's like lights off. Does it seem particularly dark in here? Why is that? Is there some lights that are off or knocked out or something? Anyway, it's not just me? Is it the time change?
There's less sunlight.
Oh, all right. Right. Done. Okay. So here's something that's rolling forward, so the center of mass is like that, and let me make sure that I have the proper rotation direction here. It's rolling forward like that. So let's talk a little bit about what it means to roll. Rolling is kind of an interesting motion. It's kind of the best of both worlds with both static and kinetic friction. Now, you might immediately think, oh, okay, that's got to be kinetic friction because you're moving across the surface. But rolling is distinctly different from dragging, right? That's when there's clearly some rubbing of the object and surface across each other. That's not what rolling is. In rolling, you don't do this. In fact, what happens is that the, let me see if I can do this better with my hands. Here you have the surface, it's lying flat, and what happens when you roll is that the object comes down, touches, and lifts. It never goes like that, right? Comes down, touches, lifts, and then the next part, touches, lifts, okay? So in a certain sense, it's more like static friction in that there is no rubbing of the surfaces across each other. It's just any given part of the wheel touches, lifts, touches, lifts, touches, lifts, okay? So it's kind of the hybrid of those two types of friction. We sometimes just call it rolling friction. So it actually has more in common with static friction because you touch, and rolling is when you're not slipping against the surface. This is, by the way, the principle behind anti-lock brakes. So you may know anti-lock brakes, the whole point of them is that when you hit the brake pedal, you don't go like that. They do it so that you brake without letting the wheel slip. And the reason for that is because the coefficient of static friction is higher than the coefficient of kinetic friction. So you actually get better braking if you use anti-lock brakes. That's the whole reason why they put them in. What I want to point out then is that one of the things that we can describe or approximate in rolling is that the non-conservative work is 0. Because it's more like static friction than kinetic friction. If I let some object slide in kinetic friction like this, you can see that it very quickly slows down because, of course, that energy that it has is taken to heat through kinetic friction. But if we roll something, well, if I can roll it straight, you can see it goes a lot longer because it's not really like kinetic friction. We're going to actually neglect the energy loss there completely. So obviously there is a little bit. First of all, it still has to move through the air. So the air is still air resistance, right? You have that. One of the places where there's often frictional loss is when you have a vehicle where at some point you do not want to be riding around inside this a rotating thing. You'll get really dizzy. So at some point in the vehicle, you're going to have to attach the wheel to something that doesn't rotate. And that's where you get your very conventional kinetic friction, right? So for instance, like, the axle, axle of a skateboard to the wheel or something like that. That's where you get your conventional friction. If you want to actually minimize that, you use the same principle in miniature. You put a bunch of little spheres around so that they can essentially roll around the fixed axle. These are called what? Ball bearings, right? So you're trying to use the same principle where by rolling you reduce the frictional loss. So what I'm saying is, if I had a perfectly round object, I had a vacuum, I had a flat surface, and I rolled this wheel, it would go forever. Okay? So that may be hard to believe, but the frictional losses are very minimal. So where do real wheels lose their energy? Partly is because they're often connected to an axle. Another reason is because there's no such thing as a perfectly round wheel. Okay? Oftentimes the weight means that the part of the wheel that's down gets smushed. It gets smushed and it's slightly flat. And that's where you can have energy loss. If you've ever taken a paper clip and just done this until it breaks, right? When you feel the ends, what do you notice? The ends where it broke. It's warm. So you dissipated energy by flexing the actual material. The atomic bonds got flexed. Well, that's exactly what's happening when you're smushing a bottom of a wheel. So there are these little things where the energy does leak out. I'm not saying that the wheel is perfect in any real situation, has no energy loss, but what I'm saying is that we're going to approximate that there's very minimal energy loss. Okay? And the reason, again, is because there's no kinetic friction present. There is no rubbing of the surfaces against each other. There's just a lifting, touching and lifting, touching and lifting. That's what rolling is. All right, so let's take a look at what it takes for that to happen. I'll draw the ground here. The ground is, of course, coming by at VCOM. When you're driving in a car forward at 50 miles an hour, that's the speed the scenery comes at you. Okay? And what we want to make sure is that the rim of the rotating wheel is the same. That means that if they will have no motion relative to each other. So we're trying to make sure that VCOM equals VRIM. There is no relative slipping of the two to each other if they move at the same speed. So every time a point on the wheel comes down, it is rotating with the same speed as the ground passing by. Sometimes this is the thing that we're about to derive, the relationship between these two variables. Sometimes it's called the rolling condition because it's what it takes to roll properly. Sometimes it's called the no-slip condition. So no slipping of the object against the surface. All right, so let's figure this out. The speed of the rim we can calculate. We know, of course, if this object rotates at a common angular speed omega, then you can find the point, any speed at any point that's tangential as long as we, of course, supply the radius. So this is good old V equals R omega. So defining the speed of any particular point is just specifying what radius are you doing that on an object which is rotating at a common omega. Now I'm not, of course, interested in this r or this r, I'm interested in the point on the very outside, the speed of the rim of the wheel, and I'm going to give that a special capital R. So I go over here, I put in the speed of the rim, and I'm done. So this is my equation. This is called the rolling condition, and also known as the no-slip condition. It's the specific relationship between the center of mass speed and the angular speed if you want to roll properly. If you don't want to roll properly, you don't have to obey this equation, but if you are rolling properly, this is the relationship. We said that there should be a relationship between these two things, and here it is. It turns out that they are directly proportional. So VCOM is directly proportional to omega, which means if you want to go across the surface twice as fast, you're going to have to rotate twice as fast. Right? They're linearly proportional. We said that if you want to move slow, you have to rotate slow. If you want to move faster, you have to rotate faster. And now we know they're directly proportional. Okay? So this equation, it sure looks a lot like this equation. But there are important differences. Remember what this equation was, is if you have something rotating at omega, and you supply the r value, it will tell you the linear speed of that point. This is relating two things that don't have to be related. If you look over here for this thing that was just rotating in place, clearly the rolling condition does not work. You can still, of course, use this equation to calculate the speed of the rim, but the speed of the rim does not necessarily have to be the speed of the center of mass. Clearly, this does not satisfy this. Okay? That makes sense? Okay, have any questions on the rolling condition before I go further? Okay. So let me show you another couple kind of inside tricks on how to handle rolling. These are tricks that you're really going to want to have. They're going to make your life way, way, way easier when you're working on the rolling problems in the homework. But these are things that are not available on the equation sheet. So if you want to use them, you got to repeat the steps that I just did. So let me take this equation. This is, of course, just your basic formula. But I'm going to make a couple really handy substitutions. The first of which is that I've just shown there's a relationship between the linear speed of the center of mass and the angular speed when you're rolling. Okay? So I'm going to substitute that in. And the other thing I'm going to substitute in for is the rotational inertia. Now you might be skeptical there and say, well, do I really want to commit to a particular object? Well, I'm not going to commit to a particular object, but I am going to say that my object has to be round, okay? Because round out, you need to be round to roll, okay? You can't roll a flat panel, right? You can't roll everything. It has to be round. And if you look on the table on your equation sheet, all the things that are round, they all have a very distinctive look to their rotational inertia. They are all some number times the mass times the radius squared. They're all round, so they all have a radius. So I'm going to express that like this. And that's the Greek letter in the front, which I forget what it's called, call it swiggle, is just some numerical factor. Okay? This is a number that is dependent on the particular object. So it's the object dependent. Dependent. So for instance, you can look at a solid disk, the factor is 1/2. The rotational inertia is on 1/2 mr². You look at a thin ring, it's mr², so the swiggle is 1. If you look at a solid sphere, it's 2/5 mr squared, so squiggle is 2/5. They're all some number times mr squared. So I don't want to commit to the exact number, of course, because I want to leave this general, but this is still useful to plug in these two. So let me show you what I get. So I put in squiggle mr squared here, and I put in vcom over r over here. So notice what happens here. The radius cancels entirely, and then I'll factor out the squiggle. I get this. Now, what is that quantity in parentheses? It's the translational kinetic energy. So we just found an extremely useful fact. When you're rolling, the rotational kinetic energy is squiggle times the translational. Again, this is your friend. You want to make sure that you can get this, because if you want to use it on the exam, I need you to be able to plug in those couple things and replicate that step. Okay? So this is only when you're rolling, okay? So rolling only. You cannot use it at other times. It would be inappropriate. First of all, I've assumed that I can relate the angular speed to the linear speed, even though they are generally independent. They're only related in rolling. And in fact, it is that relationship, the fact that vcom and omega are related, along with the fact that things that roll are round, that has gotten me this relationship. The fact that the rotational and translational kinetic energies also have a relationship. Okay? Okay, are there any questions on that before I do an example? Okay, so let's go ahead and jump into an example. Oh, and the other thing I forgot to mention, I guess I should put it over here, is that, of course, you have both types of kinetic energy. So Ke total will be Ke translational plus K rotational. When you're rolling, you do have both kinds. And we, of course, just proved that the rotational is just going to be squiggle times the translational. And so another expression for the total kinetic energy is just the translational 1 plus squiggle. So the 1 is for the original kinetic energy, and the squiggle is for the rotational. All right, so let's do a problem where we have this. Here's my example. I'm going to have a solid disk, and I'm going to have a thin ring, and they're going to have a race down an incline. Find a piece of pen. Okay. I'll give that the initial height of the incline is h, and I'll say they have the same mass and radius, outer radius. We'll find out if that even matters, but let's try to keep the race as fair as possible. And they both start at rest. So here's my question. First, I'm going to find how fast they are going. So just what is their instantaneous center of mass speed when they hit the bottom? That's something that energy is, of course, really good for, is to talk about trades in height and speed. This is also a rare opportunity in energy method, which normally, of course, doesn't talk about time at all. So we can do crazy loop-de-loop type roller coaster situations. But in this case, we're going to just be going down a flat incline. And whoever winds up there with a faster speed We can also reason if the vcom is larger in the same distance, it must have had a larger acceleration. And if it had a larger acceleration, not only did it get to the bottom with a faster instantaneous speed, it also must have gotten there sooner, okay? So it must have taken less time. So I'm going to use who's going faster at the moment they hit the bottom as a proxy for who got there first. I just want to find who's the winner of this race. So whoever gets to the bottom with a faster speed also got there first. So I'm going to figure out the winner of this race.